So, welcome to the physics seminar today. We have the great pleasure to host Coyne from the University of Diagrams. He's already waiting for his presentation. So let me say a few words about Robert, about his academic steps and research activities. So Robert is bachelor and master in physics in the University of Massachusetts, Dartmouth. Then PhD in physics in the George Washington University. And the postdoctoral research associate with the Department of Physics and Astronomy in Texas Tech. And then she went to Rhode Island as a lecturer, and now he's a physics professor there. So he has gained many awards and honors during his career, and he's a member of many different scientific societies. His research interests revolve around gravitational wave astrophysics, gamma ray astronomy, data analysis, and physics education. Today, he will talk about a recipe for unraveling the post-merger mystery of gamma ray bursts. Thank you very much. The stage is yours.
Hi, everybody. Thank you for coming. I really appreciate you taking time out of your Thursday afternoon. FYI, I'm loud, so if you came here to nap, you might want to leave. So quick show of hands real quick. We're going to do a modicum of audience interaction here. How many people know a thing or two about physics? Good. I hope that's everybody. Otherwise, we're going to have a problem. Keep your hands up. Keep your hands up. Okay. Now you can keep your hand up if you are an expert in either gamma ray astronomy or gravitational waves. Anyone here an expert in both? Great. Hopefully no one will be completely bored here. So I'm assuming you know nothing about gamma ray bursts. So we're going to go on a historical journey to capture what these events are before I can tell you about the research that's happening in the LIGO-Virgo-Calgary collaboration to help unravel the next big mysteries in their construction. And to start, we're going to go all the way back to the 1960s with that little dodecahedral satellite up there. That is one of the many Vela satellites that went up to enforce the US-Soviet Union partial nuclear test ban treaty. Basically, we were worried that each other were going to be testing nukes. And so we sent up gamma ray detectors to detect the flashes. And good news, there weren't many nuke testings at the time. Even better news, they detected this in around 1967. What you're seeing here is a light curve. The vertical axis is number of photons per second, but you can roughly think of this as brightness. And this is time, where 0 represents the moment something interesting happened, aka the trigger time. What was shown here was a brief flash of very high energy photons in the gamma ray portion of the spectrum. This was very quickly identified as not being terrestrial in origin. It was something astronomical, although it didn't make it out to the scientific community until several years later when this was finally declassified. But this event was interesting enough that there were high energy phenomena out there in space where we were producing extremely high energy light. This was so interesting that in the 90s, scientists proposed and then launched the Compton Gamma Ray Observatory burst and I don't even remember what that's called anymore. BAPSI. Oh no, Zoom's in the way. Burst and transient source experiment. This was a dedicated device that was going to look for these bursts of gamma rays. What can I tell you? Physicists are pretty lazy when it comes to naming things. You see a burst of gamma rays, you call it a gamma ray burst. Now, CGRO, the BATSI instrument on it, saw roughly 4,000 of these events over its lifetime. And we got many, many more light curves that showed that there was a big diversity of the types of phenomena that produce these events. Some of them were short bursts of gamma rays. Some of them were a very long burst that had a big tick followed by a slow decay of brightness over time. Think of it like a flash bulb that gradually dims. We even saw events that had these strange repetitive structures, big separations and emission timescales, all sorts of strange phenomenology. And scientists really set themselves to determining what the heck are these things? Well, the first thing the scientists did is they looked at how long these bursts last. The technical term is T90. The time it takes to go from 5% of the total emission up to 95% of the total emission. You can just think of it as the duration of the burst. How long did it last? And when you plot the logarithm of this duration and you bend it into a histogram, you see that you get a very clearly bimodal distribution in duration, maybe with an arguable third mode in there. In short, these could be described according to whether they were short bursts, less than 2 seconds or so, or long bursts, longer than 2 seconds, with a sort of weird part in between that we don't quite know what it is. If you, in addition to looking at duration, looked at, say, the spectral energy of these things, the ratio of high energy photons to low energy photons, that's what's plotted on the vertical axis here, known as hardness ratio. You can see two distinct clusterings of events. This sort of suggested that there might be two different types of astrophysical systems that lead to these gamma ray bursts. So the first thing we've learned is that gamma ray bursts have different progenitors. We also learned that they're extremely bright. Here's a light curve animated as if it was coming in real time. And over here is a view of the sky, the night sky. This bright line in the middle is the gamma ray emission from our very own galaxy. And that bright flash is corresponding to this bright flash of light. You can see that bright flash momentarily outshines all other sources of gamma rays in the galaxy. So these things are extremely bright. And here's the problem with bright things. You never know if it's a dim thing that you're really close to or a bright thing that you're really far away from. So the next challenge was figuring out, where are these coming from? So here's that same picture of the galaxy taken by the Fermi Gamma Ray Observatory. So you can see our galactic plane here is bright, and everything off axis is the stuff above and below the galaxy where things are really, really, really far away. If these gamma ray bursts were galactic, you would expect them to fall right along that line. But they don't. Gamma ray bursts are roughly isotropic on the sky, equal likelihood of happening anywhere that you happen to look, which suggests that these things are not galactic in origin. So we know that they're far away. How far away? Well, for that, you'd have to go to the late 90s with Beppo-Sachs and Hetty. These were X-ray satellites that were capable of obtaining precise localization on the sky for where these events were happening. This is a picture of the first gamma ray burst with a measured distance. This is by the Beppo-Sachs satellite. And for those of you who have taken your cosmology course here, you know that the universe, you probably know that the universe is expanding, and that the further away something is, the faster it's expanding, and we can measure that via redshift. Same basic idea, the redshift you learned about in introductory physics. This redshift, signified by Z, was about 0.835, not far away in the cosmological scale, but very far away in terms of practical distance measurement, over 6 billion light years. Okay, now we have a distance. So we can figure out how much energy this thing would have. And if you do that correctly, if you take the energy, that like the brightness that you see, correct it for distance to get an estimate of the total energy emitted. If you assume that's isotropic, meaning it's the same in all directions, you get a number that caps out at about 10 to the 54 ergs. I think people know what an erg is. Yeah, like 3 of you. So let's put this in context for a second. So let's pause for a sense of scale. This is the sun. Its luminosity, meaning its brightness, its intrinsic brightness, is about 4 times 10 to the 33 ergs per second. So if you look at the total amount of energy the sun emits over the course of 100 years, a century, you get 10 to the 43 ergs. Well, that is about 11 orders of magnitude off of what we're talking about. So let's go bigger. Let's talk about the whole Milky Way galaxy. Its luminosity is about 10 to the 43. So if you look at the Milky Way over 100 years, you get something like 2 to the times 10 to the 53 ergs. We are still a factor of 5 away. So somehow a single thing happening in space produce more energy than 5 Milky Ways do in a century. That doesn't sound right. So clearly the emission is not isotropic, it has to be beamed in some way. It's the only way we can make this energy argument make sense. So we know now that gamma ray bursts, in addition to being very bright, are also very tightly beamed and very far away. So where do we go from here? Now we get into the early 2000s, around the time when some of the undergraduates in the room would just about start to be born. This is the era of modern gamma ray observing with satellites like Integral, Swift, and Fermi pictured up here. Now, a couple of interesting things happened. One of them is that the Swift satellite actually has 3 instruments on it, one sensitive to gamma rays, one sensitive to X-rays, one sensitive to ultraviolet and optical light, was able to track the brightness evolution of these things over its entire lifetime. So there's a bright flash of gamma rays, but that quickly goes away. As the explosion that's happening gradually cools off, you gradually get lower and lower in the electromagnetic spectrum. You go from gamma rays to X-rays, to ultraviolet to optical, all the way down into the radio at the other end. This plot here is categorizing what your typical X-ray brightness looks like. There's some bright emission at the start, and then there's a rapid fall off in brightness after the explosion is passed. There's usually then a gradual dimming period. We'll come back to this picture. But right now, I actually want you to look at this moment here, where that gradual decay of the portion that we call the afterglow dips off and suddenly falls off very quickly. This point is something called a jet break. If you've taken any kind of special relativity course, particularly in electrodynamics, you will note that when you are accelerating a charge, for example, and you are producing electromagnetic radiation because of it, the closer you get to the speed of light, the tighter that radiation is beamed. So if you compare that cone of emission, the tightly beamed jet, and you imagine there are charges in here that are being accelerated by the explosion to produce light, you can imagine a scenario where those particles were moving very relativistically, very fast. This would produce additionally tight beaming from their electromagnetic emission. But over time, they're going to slow down. They're going to radiate energy away. So that tight beaming is going to gradually get wider and wider as the particles slow. Well, eventually, your particles are going to slow enough where that relativistic beaming extends past the cone of light that you're seeing. When you do, suddenly you're not getting 100% of the photons anymore. A lot of them are being bled off at other angles that you're not seeing. This moment is what constitutes that jet break, which means that these things are also ultra-relativistic. Woo! We've learned a lot about gamma ray bursts over the first 50 years of their discovery. What do we know so far? Well, roughly bimodal in duration hints that there are different systems that create them. They are extremely bright, not galactic, and very far away. But we also know that they're tightly beamed and are extremely relativistic. Great. What's left? The actual thing that happened. So there are 2 working models for gamma ray burst emission. One of them is certain exotic types of massive stars collapse. Their cores fail to be able to produce the outward pressure that keeps the star integral. When that pressure goes away, they collapse, commonly known as the sort of systems that would lead to a supernova. We'll say hi to Professor Cavaglia if you're more interested in that. This process of core collapse could theoretically produce these gamma ray bursts under the right conditions. The other type of system would be neutron stars that are bound together, say 2 of them in a binary system, that are orbiting, getting closer together as they radiate energy away before eventually colliding, causing again one of these explosions. It doesn't necessarily have to be 2 neutron stars. You can imagine a scenario where like a neutron star crashed into something else, maybe a black hole, something like that. But realistically, you need to have at least one neutron star involved to be able to get the types of energy that we see. And this is the one that's interesting because we are able to show this connection by looking at gamma ray bursts and then looking for signs of a supernova, which we found, hooray. This one, though, is harder. And in fact, here are some examples of abstracts that I have submitted over the course of my career with certain phrases highlighting, like direct proof of GRB progenitors is still missing. We frame this discussion around a fundamental open question in astrophysics. Blah, 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 blah. Hope you get the point. Thankfully, right around the time I got the job at URI, this happened. This is the Laser Interferometer Gravitational Wave Observatory, and I'm going to tell you how this revolutionized our understanding of gamma ray bursts. But first, we're going to pause for an intermission, because I need to talk about how this differs from the other satellites that you've seen. To understand, Professor Cavaglia gave a 10th anniversary talk recently. Some of you may have attended. So hopefully you know a thing or two about gravitational waves. But we're going to pause for that intermission because who here has heard of the rubber sheet analogy? The idea is like, yeah, Einstein's relativity can be imagined like a rubber sheet. You put a big bowling ball on it that bends the trampoline, you roll a ping pong ball across it, and it goes, woo! And that leads to things like orbits. This is a divisive analogy. So I'd like everybody in the room to weigh in. You can keep your hand down if you really don't care. If you like the rubber sheet analogy, give me a thumbs up. And if you don't like the rubber sheet analogy, you can give me a thumbs down. I would invite everybody to please vote. Otherwise, I'm just going to stand here in silence for the next 40 minutes. All right, let's go ahead. Thumbs up, thumbs down. Oh yeah, sideways, that works too. All right, I'm seeing a fair mix. Would somebody who said this be brave enough to tell me why? Yeah.
This is only occurring in two locations.
Absolutely. It's an oversimplification of a complicated problem, right? My favorite criticism of this is that you need gravity to explain gravity. What pulls down the bowling ball? Gravity. I thought we were trying to explain gravity. It's flawed. It's a flawed analogy, but all analogies are flawed. If you're taking Professor Cavaglia's general relativity class, you might have seen something that looks like this. This is the Schwarzschild metric for Schwarzschild black hole. This is in four-dimensional space-time. We've got our time component, our radial component, our angular components. Now, what we do in a situation like this, we have a complicated four-dimensional space-time. That's annoying. I can't put that on a slide. So what I'm going to do is I'm going to choose a specific orientation. Say, I'm going to go down from the pole to the equator, and I'm going to choose a moment in time. I'm going to take that, my theta is pi over 2. I'm going to take my time as a constant. This reduces my four-dimensional metric to a two-dimensional metric. I can then plot that two-dimensional metric using an imagined third dimension as curvature. That gets you this thing, which is called an embedding diagram. And this is why the rubber sheet analogy exists. Of course, I probably don't need to get into those weeds if my only point is to convince you that that rubber fabric can wiggle and those wiggles are gravitational waves. But nevertheless, that's my favorite hill to die on. So these ripples in the fabric of space and time produce predictable effects on anything with movement. If I took a gravitational wave and I passed it straight through a ring of bowling balls on the floor, shown here, those gravitational waves, given the right polarization conditions, would induce alternating oscillations in that mass distribution. It would stretch one dimension while it squishes the other, and that would oscillate indefinitely. Of course, building a detector out of bowling balls on the floor doesn't seem very practical. It would be much easier to just put two perpendicular rulers and look at how those stretch and squish. And if that sounds simplistic to you, you are correct. It's also exactly what we do. This is, in fact, the Laser Interferometer Gravitational Wave Observatory, but because that's a mouthful, we call it LIGO. There are two of these sites, one in Livingston, Louisiana, and the other's in Hanford, Washington. And this observes the universe in gravitational waves alongside our international partners, Virgo and Cagra. Now, the way this ties into our gamma ray burst discussion is this event here. I'm going to show you some real gravitational wave data down on this panel. alongside some real Fermi data up on this panel. This one's just going to be a light curve, the same thing we've seen before, where there's just kind of noise until suddenly there's a burst of gamma rays. Down here, it's going to look a little different. We're plotting frequency versus time, and this is going to be shown as a spectrogram, a map where color corresponds to how much power or energy is hidden at a given frequency at a given time. I'll be able to, if I unmute this. No, then I'd be able to hear myself. That'd be terrible. Normally, you'd also be able to hear this, but instead, we're just going to see the telltale sign of a binary neutron star merger, tracing out this chirp-like pattern, and then 2 seconds later, a bright flash of gamma ray bursts. This event is known as 170817, which follows the naming convention we use for gamma ray bursts. First 2 digits are the year, next 2 digits are the month, and the final 2 digits are the day, where the letter just tells you is it the first, second, or third event that happened that day. So this happened on August 17th, 2017. Here you can see that same plot where this is a clear evidence of a binary neutron star merger. And then 2 seconds later, in a combination of Fermi and integral, we see a flash of gamma ray bursts corresponding to a gamma ray burst. This event was so noteworthy that over 70 electromagnetic observatories spread all over the world followed it up. It was probably the most well-studied multi-messenger event in the history of multi-messenger events, which, by the way, is a field that's basically only a couple decades old. Count neutrinos. And this was the direct proof that we needed, that at least some gamma ray bursts come from binary neutron star mergers. So now we can finally start looking towards the real science that's happening right now. So let's talk about where we are and where we are going. Remember this picture where I talked about those 2 progenitor systems that could lead to this gamma ray burst? There are a lot of search techniques that we can use to search for these events in gravitational waves. On the one hand, for the binary mergers, these, as it turns out, are very easy to model using relativity. This is a calculation that most students can do at the undergraduate level after you've taken a general relativity class. You can take 2 point masses, watch as they rotate, calculate how much energy they should radiate away through perturbations in the gravitational field, and you get a waveform that, for a very well-behaved system, might look like this, where what we're seeing are the oscillations that would be induced in that L-shaped detector, where strong peaks represent lots of stretching and alternating back and forth. Now, when you have a good model for your gravitational wave, you can use our optimal search technique known as matched filtering. Now, what this does is it basically takes that model, that template, that magenta line shown here, and compares it to our data. Now, mostly the data is just noise. There's nothing interesting in there. But as you're sliding it along, what you're doing is you're comparing how well you're basically taking an inner product. You're comparing how well that template matches the background. Normally, it doesn't match well at all until eventually you have situations where you see that peak. Well, if I scrub this back here, when I look at that peak, come on, you can do it. I believe in you, PowerPoint. Yeah. If you squint, you can actually see how, to the naked eye, it basically just looks like noise, but that magenta line actually lines up exactly with the little striations in the background data. Realistically, as far as the sensitivity point of view goes, you really can't do better than match filter. Now, the other type here, supernovae, that's a little bit more tricky. You can't really get as precise a model as supernovae or core collapse, because those are much more complicated systems. It's not just 2 point masses orbiting each other. It's a giant complex system with inhomogeneities and anisotropies in its mass distribution, collapsing in a cataclysmic explosion. You have models, they're just not good enough for match filtering yet. So in these cases, we actually employ a generic search, where we're not so much looking for a model, we're just looking for, are there places where there is more energy than we would expect there to be from just noise. So you can think about those tracks again from that 1708-17 example that give you an idea of what we'd be looking for. Clusters of bright pixels inside these spectrograms. Now, there are some differences between these search techniques. On the one hand, an unmodeled search can be used to look for everything, whereas the modeled search can really only be used to look for binary mergers. Now, binary mergers in general are thought to be associated with shorter gamma ray bursts, things those less than 2-second ones, although it's not a perfect relationship. There are also some fundamental differences in like how much of the data you look at. For example, the binary merger you would expect generally to occur a couple of seconds before the gamma ray burst. So if we have, say, a trigger for a gamma ray burst, we only look maybe 5 seconds before and 1 second after, because that's where we would expect the signal to be. For core collapse, it's messier, so we have to look at a bigger window. These all have impacts on our search sense. Here is a short history of gamma ray burst searches that I have been associated with in the LIGO scientific collaboration. This first one, technically only kind of associated with. This was gamma ray burst 051103, which is a really interesting event because that red weird shaped box there, this is a picture of the sky. These are celestial, latitude and longitude basically. And this is showing you a picture of the sky, and that red box is where we figured out that GRB was based on the gamma ray observations. This big black dot is a nearby galaxy. In fact, that galaxy was close enough that if the gamma ray burst happened up here and was associated with that galaxy, LIGO would have been able to detect it. It would have been incredible. Would have won a Nobel Prize. It would have been the first detection of gravitational waves back in 2005. Except, we didn't realize it until 2012. We missed it by like 7 years. That's kind of a problem. My very first LIGO poster was on fixing this problem, by the way. I was involved in some science runs. This was before the first detection. Our 5th and 6th science runs, we did a search for gamma ray bursts, as well as a less exciting Astro Watch period. Those links are there if you're interested. But really, the meat comes after that first detection, from 2015 on, with our 1st, 2nd, 3rd, and 4th observing runs. 4th observing run is ongoing right now, and we haven't published it, so I can't tell you a lot about it yet. But some other interesting events here from our 1st observing run was this event here, another scenario where the GRB was localized to within a couple of galaxies, including NGC 3313 up here, that were close enough that we would have been able to detect it if it happened. Unfortunately, it didn't happen there. O2 is, of course, 1708-17A. That's the one we did detect. The only one we've detected so far, but we're working on it. There's a wonderful story here about how we were able to follow it up and how SWOPE was able to get the first optical detection here. It's basically because this event happened to be in Virgo's blind spot at the time. That coincidental piece of data allowed us to localize it well enough that when coupled with the Fermi observation, narrowed it down so optical telescopes could find it, which was awesome. Made most of our careers. O3 is the last published set of results. Here's that same histogram of duration versus number of GRBs. You can see hints of that same bimodal distribution here. These are the GRBs that happened during the 3rd observing run. You can see the short ones that we would target for binary neutron star analyses. We can see the long ones, which would be those collapsar models. And then this group in between where we don't really know what they are, so we just pretend like they're short GRBs, just so we don't miss anything. Those results from O3 were less interesting than 1708-17 because we didn't detect anything. So what we did was we set upper limits. These plots here are from that result. There are 2 relevant plots. The one on the left here is basically showing the statistical significance of each event. The black line represents what you would expect to find when you run this analysis on this many events for that much time. Basically, each event gives you a p-value. What's the statistical significance of this one event? You do that for all of the events and you plot them here. And the black dashed line is where you would expect it to be if there was no signal, if it was just noise. These dotted lines here are the 90% confidence intervals that kind of give you a bound for like a 1.5 sigma bounds and what you'd expect that to be. All those blue dots fall very comfortably in those 90% confidence intervals. So this is consistent with the null hypothesis. We didn't see anything. But even if you don't see anything, you can still set limits on what you might have seen. So you can convert this statistical significance into something called an exclusion distance. We know that this event had to be further away than this distance, otherwise we would have detected it. And as you can see from this plot, if we follow the blue line, which is for binary neutron stars, most of our events we would have been able to detect out to 100, 150 megaparsecs. Pretty far, but not super far. You can do the exact same thing for those unmodeled burst searches. Same statistical plot on the left. There are more dots because we run the burst analysis on more events, but still entirely consistent with there not being anything present in the data. We convert those into exclusion distances as well. We do that using different models, the details of which are not particularly interesting, but I'm happy to talk about them. But because these generic unmodeled searches are less sensitive, we get exclusion distances that are about an order of magnitude lower. Okay, great. So this is the span of GRB science that has been done by the LIGO scientific collaboration up till now, with one important caveat. This is only half of the sort of parameter space that we like to search through. And to see what's missing, we're going to go back to that canonical afterglow. Remember that X-ray light curve where we talked about jet breaks? Turns out that is connected to what happens after the gamma ray burst. And there are a whole bunch of possibilities. You can get a direct formation of a black hole. You can form hypermassive neutron stars that persist for a short amount of time. Semi-stable neutron stars that exist for longer but aren't stable, or a stable neutron star. We're going to really focus just on those last ones that stick around long enough for us to really have a chance to detect them. And if we look at that exact same X-ray light curve, we notice that there's a period here, place here in the middle, where the brightness is basically flattened off. This is not typical of explosions. Usually explosions are bright flashes and then they dim. They don't stay bright. In order for it to stay bright, there has to be some source of energy that is continuing to be injected into this explosion. One example of a system that could do this is a magnetar. This is a highly magnetized neutron star that is rotating very rapidly. Dipole emission from that rotating neutron star would produce electromagnetic radiation that would go out into this explosion and continue to inject energy into it. If that magnetar were to become deformed in some way, say, for example, stretching out one axis and making it something like a cigar shape, it would be a very strong producer of gravitational wave. And if you look at the time scale over which this plateau phase exists, it's much longer, 100, 1,000, even 10,000 seconds long. Now, if you go back to our little model here of what we searched for so far, there's another axis that I've covered up. Short duration events are like the ones we've been talking about so far. Then we also have long duration events, things that persist for a very long time. So much time they're effectively continuous. They're always there. These are like single pulsars that are just rotating around here in our galaxy. There's also this vertical axis of systems that are well modeled versus unmodeled. And unfortunately, those magnetar systems that I was talking about fall right smack dab in the middle of this diagram, and none of our tools are well equipped to search for them. Hence, we finally get to the cocoa part of this recipe. Now, key to the analysis technique I'm going to show you is the short Fourier transform. This is a contrived example just to illustrate what it looks like, but the basic gist is you take some time series data, and you chunk it up. Take the first chunk, do a Fourier transform. Do the next chunk, do a Fourier transform. Do the next chunk, Fourier transform, and so on and so forth. Now, as you can see, over time, the signal that I've artificially shoved in this data, its peak is migrating. If you take that migration of that peak and you flip it around so you can plot this as frequency versus time, that's exactly those spectrograms we were looking at. Now, if you take one of these spectrograms, you can do data analysis with this. One dumb way to do it is to just cross-correlate. Cross-correlation is a really fancy way of saying multiply together. So we take the first cell and we multiply it by the second cell. Noise cancels with noise, signal adds with signal, so you get something that's bigger. You repeat this process for the second one, great, and you just add those up. Now the trick here is this is just the cross-correlation statistic. Fourier transform 1 multiplied by Fourier transform 2 divided by the time window that you use. You were just literally adding them up into a detection statistic. The trick here is that if you tried this with the next chunk, you'd be multiplying signal with noise. That wouldn't give you anything. So you artificially shift the signal, so you're multiplying signal with signal. The way you know how to do this is you use a model to inform you how you expect that signal to evolve. You repeat this process, and eventually you add up all of the signal information with none of the noise, or with less noise than you would normally have. This is the cross-correlation algorithm, which was backronymed to COCO, which is in the title of this talk. Now, I'm going to give you a quick rundown on how this works, and then I'll show you the results, and we'll call it a day. Here I'm taking two detectors, say the LIGO in Livingston and the LIGO in Hanford. It's an astrophysical signal. We would expect the signal to be in both. And just for the sake of illustration, I'm going to take those two data streams and shove them together into one. And now I can just label all of the bits. Nothing fancy, just looking at both detectors. Now, we have a choice in how we do this cross-correlation. The least sensitive limit is we just compare the first spin in the first detector to the first spin in the second detector. Boom. And we cross-correlate those. Then we do the next one, the next one, the next one, and the next one. The nice thing about this is that you don't have to do any model shifting. You're always multiplying signal with signal, assuming you cut into the start time. Now, the good news about this is it produces very predictable statistics. Just get Gaussian, standard normal distribution if there's no signal. You get another shifted Gaussian distribution if there is a signal. So you can set some statistical threshold, say what your, I want to make sure I catch some percentage of all of the real signals and I don't introduce any false alarms. And the nice thing is that the statistics work out very computationally efficient, but not very sensitive. Doesn't need a model, but it does not give you good sensitive results. The other extreme, you can cross-correlate all possible pairs. So I do the first with the second, first with the third, fourth, fifth, sixth, seventh, eighth, ninth, and so on and so forth. I add all of these up. And then I repeat the process for the second column and the third column, and I just add them all up. Much more complex, but much more sensitive. Does change the statistics. The details aren't super important. Get a chi-squared instead of a Gaussian. These are still well-defined statistical distributions that you can set thresholds on. The benefit here is, although you need model predictions in this case, you get a highly sensitive search. This is actually equivalent in sensitivity to a matched filter. Hence, we call it the matched filter limit. But the power of this approach comes in the in-between. When you are doing this in a semi-coherent, you once again chunk up your data. You say, I don't trust my model that much. I only trust it a little bit. I trust it for maybe 3 time bins. So I do a matched filter limit on all of the time bins in that coherent chunk. And that gives me my first part of my detection statistic. I then shift my chunk over. I repeat that process, blah, 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 blah. And that gives me the second chunk. I do it for the third chunk and the fourth chunk and so on. Changes the statistics once again. Everything remains well described though. And the nice thing about this is you can change the sensitivity of your search by shifting that coherence window, how long you are willing to trust your model for. At the low end, you end up something like this. And at the high end, you end up something like this. This plot here shows you the sensitivity basically we're looking at the weakest signal that could be detected as a function of your coherence time, which is how long this coherent chunk is. More coherence time means you can detect weaker signals with higher significance. The nice thing about this technique is that although we are interested in applying it to this magnetar model, you don't need to. It's completely model agnostic. You can take any model you like, feed it into this, and it works just as well. So as a proof of concept, we looked at 1708-17. Now, for some context, that 1708-17 event was about 40 megaparsecs away. As far as gamma ray bursts are concerned, that's basically right next door. There were searches for so-called post-merger emission, meaning what happened after that gamma ray burst, by LIGO Virgo cockroach. But those were really able to reach out only to distances of something like 4 or 5 megaparsecs, about a factor of 10 off the distances that we need. Now, the good news is that because COCO is model informed, we are slightly more sensitive. The bad news is we couldn't get to 40 megaparsecs either, at least not in the operational least sensitive limit of COCO. We were able to get out to distances of like 10 to 15 megaparsecs. Better, but not 40. But as a proof of concept, it illustrates the benefit of this approach. If you have an emission model that you trust, and you have a signal that you can analyze, you can leverage that model prediction to get more sensitive. Ooh, the next slide is incredibly overwhelming. I'm not ready for it. I'm gonna take a sip of coffee. Now, the question becomes, what's going to happen in the next few years? Right now, LIGO is operating during its 4th observing run. On average, we can detect binary neutron stars out to something like 170, 180 megaparsecs, pretty far. But we're not quite to what we call design sensitivity yet. That's going to theoretically come with our next observing run sometime in the next few years. So what we did is we took this magnetar model, and we looked at the parameters that define how the system evolves. These are things like the radius of the magnetar, the strength of the magnetic field of the magnetar. And we took that and expanded it into a parameter space of all possible signals that could exist. And what we did was we asked, okay, if I choose a point in this parameter space, how far would I expect COCO to be able to detect a signal out to that distance? We did it in each of those 3 limits I talked about. Stochastic, match filter, and semi-coherent. These grids that are incredibly hard on the eyes is conveying that information, albeit in an incredibly inefficient way. Let me try to break this down. Each one of these 3 basically showing the same thing. On the horizontal axis, these are radii of the magnetar in kilometers. So the left side is 12.1 kilometer radius up to 13.9. Vertical axis is the strength of the magnetic field. Take this number, which ranges from 0.34 up to 4.76, multiply that by 10 to the 14 in Gauss. Now, each of those signals lasts for a different amount of time. There are basically 3 different timescales: 165-second signal, 256-second signal, 512-second signal. That's what those numbers are. But the important thing is the color. Okay, that's the important thing we're looking at here. For the stochastic, the poorest performers are in red, the best performers are in blue. And detection ranges in that least sensitive limit go from about 42 to 48. These numbers are all very close to each other. That's why this looks, the heat map looks scattered. It's because they're all right around 40-ish. Good news, that's how far away 1708-17 was. So at design sensitivity, we would probably be able to detect 1708-17. 10 years later, boom, maybe the universe would be nice to us again. The other extreme, say match filtering, we're getting much better results. These are actually distances from like 190 up to 270 megaparsecs, again going from red to blue. That's incredible, it sounds great, except it's also completely unrealistic. Our models are not good enough to be able to trust a match filter. If they were, we would just run a match filter. But We can't, so we won't. The important thing here is what is the middle ground? The part where it's more sensitive than stochastic and less sensitive than match filter. Here at design sensitivity, we're still getting very robust numbers between 90 and 130 megaparsecs. This is realistically something that would be astrophysically relevant, meaning if we were to detect a gamma ray burst during in LIGO, Virgo and Cobra, during our next observing run, we could conceivably constrain what happens after that gamma ray burst using this method. Now, I would love, absolutely love to give you the most up-to-date information here. Unfortunately, it's not published yet, so I can't. What I can do is I can recap where we are, talk about a little bit of what's left, and then in my last 2 minutes or so, I want to give a sales pitch about the broader, it might be my other hat that I wear. So to remind you, what did we learn? Gamma ray bursts have multiple progenitors, they're extremely bright, they're not galactic, and are extremely energetic. They're tightly beamed and extremely relativistic. Since then, we've also learned that their progenitor systems include both binary neutron star mergers, which are excellent source targets for gravitational wave analysis, but also collapsars leading to supernovae, which is another active field of interest, some of which is happening right here at Missouri S&T. Gravitational waves have the capacity to unlock this next step in our understanding of these events by getting at the central engine that drives this late time emission and their afterglows. But we're still learning more. One really great example that undermines a vast majority of the work that we've done so far is this event right here. This is gamma ray burst 211211A, December 11th, 2021, aka my birthday. This event right here, super interesting. This came out of a Nature paper. Most gamma ray bursts don't get a Nature paper. So what's the issue? Remember that by modality I mentioned in duration and hardness ratio, and how we can use that to guess what the progenitor system is with short gamma ray bursts that have high energy photons being likely to be caused by binary neutron stars, and long soft events being likely to be collapsars. Well, this event, which had a kilonova associated with it, which told us confidently that this was a binary neutron star, lived smack dab in the middle of the other part of that distribution. Which means, had LIGO been observing at this time, we wouldn't have got to analyze this until we saw the kilonova. This is a problem. That's the problem with bimodal distributions in general. They overlap into each other, and it's hard to draw a firm line of where that is. Just assign probabilities. Thankfully, there are numerous metrics that we can use to try to tease this information out. If you're interested about those, ask me about it later. And although I can't talk about them today, I am pleased to report that our current suite of analyses for our current observing run, set to end about 1 month from now, those are ongoing. We expect them to come out soon. So even though I can't tell you about them now, I will be able to share with you a draft of the paper once we finally get it finished, sometime between now and the heat death of the universe. So that about takes up my time, but I'd like to take a brief moment just to put on my other LIGO hat, which is as it's the chair of the Communications and Education Division. We are currently in a somewhat unprecedented period of publication in the LIGO Scientific Collaboration. Over this past summer, we tried to get something like 24 papers out. We managed to get about 2/3 of that number. And over the span of the next 6 months, we're going to try to publish 50 more. And then the next 6 months after that, 50 more. And I'm probably going to die from exhaustion about halfway through that process. That is not the slide I wanted to go to. The first big summer event was this one right here. You might have seen this poster plastered around somewhere from the LIGO group here. This was 231123, the most massive binary merger to date. Black holes that are roughly 100 and 137 times the mass of the sun spiral together to create an absolutely gargantuan black hole, about 225 solar masses. I will say that this is peanuts with respect to supermassive black holes, but as far as stellar mass black holes, we have yet to find anything bigger than this yet. After that, in August, we released an update to our gravitational wave transient catalog, and we went from this many events over our first 3 observing runs to that many events, more than doubling the number of black holes and some events with neutron stars here. To look at this graph, these blue dots are mergers of black holes. The dark orange are neutron stars that merge sometimes with black holes and sometimes with other neutron stars. And red and yellow are sources that have been detected through electromagnetic means. And then, of course, most recently, the 10th anniversary of the first detection, where interestingly enough, oh, I didn't actually put the video in. We got our loudest event to date, which was a carbon copy of the first event. Same masses, same distance, but whereas the first event back in 2015 was a signal to noise ratio of about 30, this one was about a signal to noise ratio of about 80. And those improvements were entirely from improvements to our detector. So I'm going to go ahead and stop talking now, leave a little bit of time for questions and discussion. Thank you for coming, and yeah, I'm done.
Thank you very much, Rob, for the night. Very live today. So let's start with questions from students.
In the first detection event that you had talked about, there was a 2-second delay between the actual gamma ray burst and the event. LIGO, why 2 seconds?
There are a bunch of reasons, but the simplest one is the gravitational waves actually peak shortly before the collision. Then there is the collision, followed by an explosion, and the time scale of that explosion can roughly be understood to have taken approximately 2 seconds.
Okay.
There are some more advanced things like time dilation near to the source that makes it slightly more complicated, but it is literally just difference in the time scales when the initial.
Okay, but the waves are still traveling in.
Yes, in fact, that event was a very good stringent test on the speed of gravity versus the speed of light, because even if you take that delay of 2 seconds, even if you correct it for relativistic effects, and you attribute all of that time delay to the difference in propagation speed, it still turns out that there's like 99.999999999% in agreement. So some of the strongest evidence that we have on the gravitational wave side for comparing the speed of light.
You mentioned that the statistical method is determined by how much you trust the model you're using. How do you determine how much you trust the model?
Yeah, so that is a great question to which there are varying degrees of confidence in the answer. Some models you can just kind of tell are overly optimistic. One of the best examples of this is the accretion disk instability model that we tend to use to look at these sources of sort of long duration emission. Whereas, like, if you actually trust the model, we should basically be able to detect every accretion disk instability that's ever happened. Just an overly optimistic model. Since we haven't detected it, that's evidence that it's a little bit overly optimistic. But the truth is, you genuinely don't know. You can make some estimates based on, say, the complexity of the system versus how long you would expect the approximations you make in the modeling to last. But even then, that can just get you to within a ballpark. So the truth is, you basically try to do the most sensitive search that your computational resources will allow. Because even if you misjudge how much you trust the model, that increase in sensitivity is going to outperform the losses that would come from missing the signal. So realistically, if we could run a match filter, that would still be better, but the computational cost of that would be completely prohibitive. So you make some reasonable estimates for what you think you can do computationally, and that kind of sets your upper limit in practice. Realistically, we have to get at least one detection of these to be able to properly gauge what our, how good our models are. Because one way you can conceivably do this is, let's say we do have a very nearby TRP that's within our horizon distance. You can now basically test this at various coherence lengths and figure out where that bifurcation happens. But we need a signal to be able to do phenomenological tests like that.
you mentioned that the beam that is coming, it's like the gamma ray burst beam, and one of the reasons was the EM radiation. What was like the plan?
Yeah, so I mean, realistically, the original justification for why gamma ray burst would be purely from a energy budget standpoint. It really is just that a single star exploding can't reasonably be expected to produce more energy than all the stars in the Milky Way over a century. That was the beginning of it. Now, there are some additional sort of like physical justifications, particularly in systems that have strong magnetic fields, like some of these are expected to have, for like how one would produce jets. The same sort of discussions that go into X-ray binaries or active black nuclei. And you can argue, I can't, but people smarter than me can argue that those types of systems ought to lead to jet formation. So that's probably supplementary, arguments for why this should be. But for example, 1708-17 actually gave us a really good measure of this, because it turns out the only way you can really explain the brightness of the GRB versus the distance and the binary neutron star is if we are viewing it, so like just on the edge of that cone. So this gave us some even better evidence that these things are highly.
Okay, next, please.
So when you were talking about magnetars and rotating really fast, they can deform a lot, which would make the gravitational waves that it produces very obvious. So if you had a side by side of a not so deformed magnetar and the other one, you could see from the gravitational wave data. Could you do the same thing with the electromagnetic wave data?
So yeah, you can reverse engineer basically from those X-ray light curves, the sort of properties that a magnetar would have to have in order to do that. This can place constraints on things like magnetic field strength, rotation rate. It is harder to produce constraints on how deformed the magnetars are, because there are degeneracies in the electromagnetic emission you would expect between the deformation of the neutron star and the strength of, say, for example, the magnetic field. Deficit in one can be offset by the other. There is no degeneracy like that in the gravitational wave signature, so that's a better discriminator, but you can get at some of this. And in fact, that's how you inform the model search. Talking about how it's computationally limited. One way you get around that by shrinking the portion of the parameter space that you're looking at, and you can set like magnetic field has to be less than this, radius should be bigger than that, based on electromagnetic observations to make it work.
Okay, let's have one more question. If there is, please.
Okay. Looks like you're always looking for patterns that you know ahead of time. Was there any discovery where you found something that you were not expecting?
Oh, God. So, I mean, yeah, I'll make a sort of joke answer to that first, the first detection. One of the things that you have to understand about LIGO is that it was originally designed with these binary neutron stars in mind. That's why the shape of the noise curves are the way they are. They're really optimized with binary neutron stars. Fact is, we're seeing a lot more binary black holes than we are neutron stars. So that surprised a lot of us. Not all of us. Some people predicted it, but most of us thought we would be detecting neutron stars. As far as like an unmodeled search, like just a blip of astrophysical gravitational waves, or indications of like a deviation from the predictions of general relativity, or some discovery that truly surprised us, the answer is not yet. But goodness gracious, I imagine I can speak for all some 4,000 members of the LIGO Virgo collaboration, where I'd say we are desperately waiting for that first thing that comes along and really surprises us.
In the alien signal, we can talk
Yeah, we can't talk, that's not released yet, Marco. I know the comments out there, but no, hopefully soon.
Okay, last question, please.
So if those signals are the gamma ray bursts are highly deep, then we see only a fraction of all the events that are out there. Is there any discussion of the population statistics that you can infer from this, and how many of this highly energetic version can?
Yes, there is in fact an extensive study on the population statistics of gamma ray bursts. And here's the most impressive thing for me. The median of their redshift distribution is around 2. By the way, LIGO can get out to maybe 0.2 at its most advanced design sensitivity. Most of these events are at cosmological distance scales. So realistically, the part of the reason we have not seen more of these is because we are sampling the nearest portion of that very diffuse and distant population. We are able to place constraints on that low end. Very depressingly, we are continuing to refine our estimates to be narrower and narrower and narrower towards the low end of that event rate, which is bad for me, but it is good science. So the people doing population statistics, it's good for that. But realistically, until we get to the next generation of gravitational wave detectors like Einstein telescope and Cosmic Explorer, we're not going to be sampling an appreciable portion of the gamma ray burst population.
Okay, so let's take our